Bond, and the topic of our research is discovering attacker cognition vulnerability from malware. Our research team includes John Olenek, I'm Ben Bond, and our advisor is Julian Rushi, and we study at Oakland University. So I'll be going over an introduction to our work, the objectives for the research, our hypothesis, and then we'll get into the elements of the paper that we're currently writing, on the malware that we're specifically focusing on, and then how we model this malware and extract cues of human cognition. So as an introduction, malware code is usually left behind in a thwarted attack when threat actors compromise a system. They write programs to do various actions on that system, and oftentimes these codes are left behind for analysts to find and analyze. And then this analysis can be useful for engaging in with these same threat actors in the future, except when the threat actors change their tactics, the analysis can lose some of its usefulness. So they can change the data structures or algorithms they use or their general tactics. But we think what doesn't change is the malware author's cognition, and over time, patterns emerge in each of their software, each of their programs that they write, no matter how they may change their tactics. So we believe if we can expand malware analysis to include the cognition of the malware author, we'll be in a much better position to engage in defensive deception and future engagement with the same author or group of authors. So in short, our objectives for the research is to reverse engineer human cognition from malware. And we'll use this analysis to guide the development of computational models that reflect this cognition as it appears in their malware. Parts of perception that we will be able to identify are perception, decision-making, problem-solving, attention, memory, and learning. Each of these elements are very important in writing malware and engaging in systems that the malware are deployed. So we want to discover innate and possibly involuntary cognitive vulnerabilities. As I mentioned, the cognitive vulnerabilities are generally unknown to people and very difficult to change. So we can exploit these vulnerabilities in future cyber deception. We believe that they'll be persistent and recurring. So our hypothesis is that threat actor cognition is reflected in the malware they write, and these appear in cues or sometimes more explicit manifestations. And the cues that we can find of these cognition are both of declarative nature. So these are types of cues found in the embedded compiled code that are discovered on compromised machines, or they're reactive, discovered in a dynamic exchange between the threat actor and the systems that they are currently compromising, the decisions that they make as they're receiving output and providing input to the compromised machine. And so our assumption underlying all of this is that there is a DNA of human cognition, meaning that one person's cognition is identifiable from another, or one group's from another, so that a profile can be built up over time to identify the specific author. So in the paper that we are currently writing with this research, we look specifically at an industrial control system targeting malware called Triton or Trisis or Hatman, depending on the literature you're looking at. And this targets industrial control systems by leveraging an exploit in the software. And this has been referred to as the world's most murderous malware because it's designed to disable safety procedures that are in place in these facilities, so that if there's some sort of mechanical error or just the facility is put into a critical state, systems are in place to prevent it from going critical. But Triton is designed to deactivate these, putting human lives potentially in danger. So obviously this is a very complex and dynamic system that the threat actors have to navigate. So they make many decisions and they exhibit learning and problem solving as they navigate the system and try to find their way in. So this interaction with the system and the mistakes they make can be analyzed for cues of cognition. And we do this by creating a stochastic activity network that is a high-level graphical language for describing system behavior. And we use this to model both the threat actor behavior and the system, the ICS system's behavior itself. So the interaction between the two groups. And there are probabilistic cases for modeling the stochastic events, so we can have a probability of success or failure at certain junctions. And we can model the Triton threat actors' activities based on the malware samples that have been then analyzed, because the code that the threat actors wrote has been discovered and analyzed using traditional methods. So then finally we'll want to extract the specific cues of human cognition by embedding a hidden Markov model within the stochastic activity network. And this way we can have the hidden Markov model observe the output of the system, the certain states that the ICS model is put in, based on the actions of the threat actor that we can't necessarily observe. So the output of the hidden Markov model will be the cues of the cognition that the threat actor is exhibiting and will find difficult to change. And here are the references. Thank you for listening to this talk.